Hi everyone, my name is Chengyang Wu from University of Pennsylvania. Today I'm going to present our paper, ADA Chain, a learned adaptive blockchain. So first of all, instead of talking about permissionless blockchains like Ethereum and Bitcoin, our discussion today focuses on permission blockchains, which consist of a set of non-identified entities that might not fully trust each other. ADA Chain also belongs to this category. Permission blockchains have enabled a wide range of applications, ranging from contact tracing to healthcare. The popularity of these services has attracted interest from both academia and industry. These are the companies that have adopted permission blockchains according to the Hyperledger project's website. And these are the range of applications being enabled. At the same time, a proliferation of permission blockchain systems have been proposed, each with a different architectural design on how to process transactions. At a high level, distributed transaction processing consists of two phases: ordering and execution. The table below summarizes the design principles of different blockchain architectures in 6 performance optimizations and 2 correctness dimensions. For example, the OX architecture, as used by Tendermint, order transactions first and then execute them in sequence. The OXY architecture, however, constructs a dependency graph after the ordering phase based on the data accessed by each transaction, and then execute independent transactions in parallel based on this dependency graph. The XOV architecture is inspired by optimistic concurrency control. Here, since execution happens before validation, before ordering, a separate validation phase is needed at last. XOV first simulates transactions fully in parallel, then order the execution results, and then invalidate all transactions that are simulated on stale data, and lastly, commit the valid transactions to database. The XOV++ extends XOV architecture by reordering transactions inside a block. The idea behind it is simple. Within the same block, suppose we have 2 transactions, I and J, and I is ordered before J. If I write to key A and J reads key A, then J is guaranteed to be invalidated during the validation phase because it is simulated on stale data. To solve this issue, we should reorder J before I. And this can be achieved by building a conflict graph that captures all rewrite conflicts inside the block and doing a topological sort. The XOV SHARP takes one step further. It keeps track of all dependencies incrementally, even for those that span across blocks. If an incoming transaction is involved in a dependency cycle, it will be dropped immediately. This way, it achieves serializability without requiring a separate validation phase. Lastly, the XOV architecture has a special implementation, the stream chain system, which fixes the block size to be 1 in order to reduce latency. The performance of this system varies a lot under different user workloads and hardware. For example, the figure here shows the effective throughput of all these architectures under 4 different sample workloads. The effective throughput only counts valid transactions. Workload A, B, C, D varies in terms of the rewrite pattern of transactions, the skewness of the keys that transactions access, the load of the system, and the computing intensity of smart contract. For the XOV plus reorder design, it performs best under workload A, suboptimal under workload B, best again under workload C, and suffers from 0 performance under workload D. As another example, the OXY architecture also suffers from significant performance variation under different workloads. And all these results suggest that there is no one-size-fits-all blockchain architecture. Obviously, for a particular fixed workload, we can easily find the optimal architecture. But what if the workload shifts permanently due to business demand? What if the workload varies throughout the day, and different blockchain instances are deployed on different hardware, or when new blockchain architectures are invented? In all these realistic scenarios, an adaptive blockchain that can switch between architecture is needed. As a Strawman solution, we can compute a static mapping from workload characteristics to the optimal blockchain architecture. And the downside of doing so is it is difficult and time-consuming to compute such mapping, and it depends on underlying hardware. and it is still suboptimal when workload shifts unexpectedly, and it requires recomputing when new blockchain architectures are invented. AdaChain takes a different approach. It uses machine learning techniques to learn the mapping on the fly. AdaChain relies on two key innovations. First, it models the selection of the blockchain architecture as a contextual multi-embedded problem. Second, it introduces protocols to switch from one blockchain architecture to another in a live system while respecting correctness and security concerns. With AdaChain, we can automatically select the optimal architecture under dynamic workloads, and it will quickly adapt to new hardware, new storage subsystems, and new unanticipated workloads changes on the fly, all achieved without requiring a separate training data collection phase prior to deployment. Now, let's look at the AdaChain system component and workflow overview. The example figure here consists of 4 servers and several clients that send requests to any of the servers. Each server consists of a native peer process that orders and commits transactions, a local blockchain ledger, and a learning agent process, which is responsible for observing the state and make decisions. Now let's look at the workflow. AdaChain operates in episodes, which is marked by a constant number of committed blocks. In each episode, the choice of architecture remains the same. For example, OX or XOV. At the first step, the native peer process notifies its local learning agent when the number of committed blocks reaches a low watermark in episode n, which is WLN in the graph. Next, the local featureizer will extract state as n+1 from blocks committed in episode n. Next, each learning agent will exchange the local throughput measurement along with the state for the next episode with learning agents on all the other servers. And the goal is to achieve agreement on these values, or we call a global value. Then the model, which is a random forest predictor, will select the architecture AN+1 for episode n+1 and informs the peer. Next, SN, AN, RN, which is state action reward triplet, will be added to experience buffer because now they are the global value, which means the agreed value. Then the model is retrained based on the experience. Note that our discussion and the yellow diagram highlights server 1 for the ease of illustration. To maintain decentralization, the yellow diagram actually is carried out simultaneously on all the servers, not only server 1. Now, let me introduce more details about the learning agent. The learning agent formulates the optimization task as a contextual multi-embedded problem, where the context or state is the recent properties of the workload and hardware. The arms or actions is one of the many blockchain architectures that we want to choose between. The reward is the effective throughput of the newly selected architecture. And the AdaChain's goal is to minimize regret Rn, which is the difference between the observed reward and the theoretically best reward. We choose this contextual bandit problem formulation because the action taken, which is a blockchain architecture, is not going to affect the state of the system, which is a workload. To solve the CMAB problem, AdaChain utilizes a technique called Thompson sampling. So traditional supervised ML training finds the model parameters that are most likely given the training data. And it only works well when the training data is a representative sample of the population. However, this assumption is not true in AdaChain because it collects data on the fly. Thompson sampling takes a different approach. Instead of maximizing likelihood, it samples from the distribution P theta given experience E, and it can be proven to strike the optimal balance between exploration and exploitation. This corresponds to step 6 in the overview figure. At the core of each learning agent is a predictive model, for which we use a random forest regressor. The input of the model is a state concatenated with a candidate action, and the output is a predicted performance. AdaChain enumerates the action space to predict the performance of each action. Note that each honest node starts with the same random seed, and this is important for achieving deterministic training and inference, and both are important for Ada chain to agree for each node in the Ada chain to agree on the same architecture in the same episode. To integrate random forest with Thompson sampling, we need to train the model as usual, but only on the bootstrap of the training data. Now, let's look at the state and action space in details. So the state space consists of explicit state and implicit state. All explicit state are measured locally by each peer via a window of recently committed blocks, BI to BJ. The red ratio is counted at the transaction level instead of record level. It is the number of transactions divided by the number of red transactions divided by the number of old transactions. The skewness is represented by frequency corresponding to the hottest key during the window. The system load can be measured by the number of requests to arrive at the system per second. And the execution delay is the average execution delay of smart contract during the window. Note that implicit states such as CPU speed, disk speed, network latency, and bandwidth, they are relatively static during one deployment. Thus, Ada chain does not require explicit synchronization of these implicit states. To represent the action space, one naive approach is to give each architecture a one-hot encoding. Let's assume XOV is represented by vector 1, 0, 0, 0. And at some point, the tree node is split by the first dimension. The left children is XOV, right children is non-XOV, including OX, XOV++, and stream chain. Note that this is not ideal because XOV++ and stream chain, they have closer relationship to XOV, but now, since they fall into the same node of OX, the performance prediction will be wrongly averaged by the performance of OX. To solve this problem, our approach is to featureize the architecture design space first. Our featureization includes three dimensions: block size, which is a scalar variable; early execution, which is a binary variable; and dependency graph construction, which is also a binary variable. Our action space consists of 100 choices, including the block size. Note that we exclude earlier abort, cross-block conflicts, and parallel execution due to the reasons listed in this slide. To actually switch from one blockchain architecture to another, we need to address three challenges. First, for the same episode, how to ensure each peer agree on the state and action. Second, how to guarantee live switching without pausing the transaction. Third, before converging to the optimal architecture, the lineage might occasionally choose bad architectures. And how do we prevent being stuck there too long? Ada chain utilizes a twin path protocol to solve the challenges. Details can be found in our paper. We evaluate Ada chain on Cloud Lab, where we set f equals 1 and n equals 4. We use effective throughput as the main metric. The specific workload configurations consist of 6 tuning knobs, and the details can also be found on our paper. We first evaluate Ada chain on the 4 different static workloads. Here, PW represents the probability for a transaction to be a write transaction. P-hot is the chance to write a hotkey, and N-hot is the number of hotkeys. N-trans transactions will be fired during T-fire interval. T-compute is the execution delay of the smart contract. For each workload, we plot how the system's effective throughput changes with the episode. In workload A, the blue line represents Ada chain, and the yellow line represents XOV++, which is the best among all fixed architectures. Ada chain can converge to this optimal architecture after a few explorations, which is the valley in the graph. Similarly, in workload B, the red line, which represents Oxy, is the best baseline. Ada chain can converge rapidly to it as well. Again, the valleys are the necessary explorations to avoid being stuck in local optimum. Now, in this table, we summarize the effective throughput for each architecture in the last 20 episodes of each workload. And Ada chain provides the best average and the best worst-case throughput across all workloads. Also, it can converge within 1 minute by average without requiring any hints provided by human experts. Now, we synthesize a dynamic workload by chaining workload A, B, C, D, and back to A in sequence, each running for 15 minutes. The left figure shows how the cumulative community transaction change with time. And right figure shows ADA chain throughput in each episode. You can interpret the left one as a CDF graph and the right one as a PDF graph. Again, although there are some explorations, ADA chain can commit to 1.2 million, which is 70% more transactions than the best baseline. More evaluation results can also be found in our paper. This concludes my presentation today. Thank you.